You are seeing my slides now, right?
Yes. Yes.
Okay, let's start. Today I will talk about convergence and consistency analysis for extended common filter based SLAM. I would say this is my favorite paper. If you look at my Google Scholar, this paper was cited by 478 papers, and the citation is much more than the other papers. So this paper proves the convergence of EKF SLAM algorithm and point out the inconsistency issue of EKF SLAM. This is an outline of my talk today. I will first give a quick review about extended common filter based SLAM. And then I talk about the motivation of the work, and then talk about the convergence, and then consistency, and finally, summary. After last few weeks, I think most of you are familiar with least square based SLAM. So let's look at this scenario. Robot starting from post 0 and observe feature 1, feature 2, move to post 1, observe feature 1, 2, 3, and then move to feature post 2 and observe feature 2 and feature 3. So if we formulate this problem as a least square problem, what we normally do is we set R0 as the origin. So R0 is not in the state vector. So the state vector or the variables are R1, R2, feature 1, feature 2, and feature 3. And the measurement we have, one is odometry from R0 to R1, R1 to R2, and all the observations from robot post to features. So we can formulate this problem as a least square problem. This is standard format of least square, Z minus Fx transpose times coherence matrix inverse and Z minus Fx. So in particular, for this particular problem, we have odometry and observations. So this Fx, the object function, contains two parts. The first parts are all the odometry. And the second part are all the observations. For odometry, we have 2 here. So this sum is 2 terms. And for observation, depending on how many, here 1, 2, 3, 4, 5, 6, 7. So this will be 7. So we sum all those terms together. That's our objective function. And it's clear that in this case, we have more measurements than the variables. So this is a standard least square optimization problem. I highlighted here R0 is often set as the origin, mainly because in Liang's talk, you probably understand we don't have to choose R0 as the origin. We can choose another pose, for example, R2 as the origin, or we can choose coordinate frame decided by 2 features. So many other ways. But in any case, the information are odometry and the feature observations. And once the variables are decided, we can formulate it as a least square problem. So let's look at another case. For example, when we have some prior information about R0. So this R0 is no longer the origin, but we have some prior information about its global position and orientation. In this case, how can we formulate this least square problem? In this case, we have to include R0 in the variables. So the variable will have R0, R1, R2, and all the features. And in this case, the measurements not only odometry and the observation to features, but also the prior information about R0 is the measurement or information. So when we formulate least square problem for this scenario, we need to add the prior knowledge about R0 as one term as well. So the odometry and observation are the same as before, but we have another term, which is prior information about R0. In a simple case, that prior is just an estimate of the post-zero. And P prior is just the Convergence matrix of this post-prior. And F prior, X, is just R0 itself. So we can add this prior information into this least square formulation. Again, we put all the information together and solve it to get the solution. So this is a least square problem, a least square formulation. And normally least squares are relatively easily to be understood than Kalman filter. Now let's use the same scenario to see how extended Kalman filter works for this kind of scenario. How to perform SLAM using extended Kalman filter for this. The same scenario. And the key point for EKF SLAM is EKF is estimating the state of a dynamic system. And this state of the dynamic system keeps changing. At the very beginning, this state is just R0, the robot pose R0. And we have the prior global information. So we have an estimate, we have a Convergence matrix as well. So that's at the very beginning. And then in this case, robot at time 0 see feature 1 and feature 2. So we need to add 2 features using the observations at time 0. So the state X become R0 plus feature 1 and feature 2. And this is called feature initialization. Feature initialization means using the observation and the current robot pose to get an estimate of the feature position, as well as an uncertainty, the Convergence matrix of those feature 1, feature 2. So this is the second step. Add feature 1, feature 2 there. And then the next step is robot move to step 1, which is R1. In this case, we use prediction to predict R0, F1, F2 to R1, F1, F2. So that's the EKF prediction step. So you can see R0 is changed to R1, but feature 1, feature 2 are still there. After this prediction, we will again observe feature 1 and feature 2 at time 1. So we will update using observations of feature 1, feature 2 at time 1. So we do EKF update. And the state is still R1, feature 1, feature 2. At time 1, we also observe a new feature, which is F3. So we need to do another step. We need to add new feature F3 using the observation at time 1 of feature 3. So in this case, we need to do another step of feature initialization. Now the state has robot 1, feature 2, feature 3. Now we have used all the observations at time 1. Now we move to next step. So it's another EKF prediction. So R1 changed to R2, and feature 1, feature 2, feature 3 are the same. Then we do the update using observations at time 2. And at time 2, robot observe feature 2 and feature 3. So we just do the EKF update using these two observations. So how to perform the steps? We follow the EKF algorithm. So for EKF, we have a nonlinear process model, we have nonlinear observation model. In each step, the observation model may be different because the number of observations can be different. If you observe feature 1, feature 2, your observation model is related to feature 1, feature 2. If you observe feature 2, feature 3, then this observation is related to feature 2, feature 3. So this can be different in each steps. In any case, we can apply the extended Kalman filter formula using the estimate and the convergence matrix in the previous step to calculate the state estimate and the convergence matrix in the next step by following prediction and then update. So once you have the process model and observation model, the main thing is calculating the Jacobian and then use those equations to do the calculation. In EKF SLAM, suppose we are talking about 2D cases. 2D EKF process model and observation model are something like this. First, the state vector, including robot pose at time k, which is the position xy and the orientation phi, and also the feature positions. Depending on how many features you have, then you have those in the state vector. The process model is written in this format. You need to remember the state vector contains robot pose and also the features. So this process model need to have robot pose and features. So in this case, the first three equations are the robot motion model, and the next 2n equation is a feature process model. Because features are stationary, so the feature at time k and feature at time k plus 1 are just the same. But you need to write the whole thing as a process model and apply this in the extended Kalman filter. You need to calculate Jacobians using this process model. For the observation model, suppose we are talking about range and bearing observation, then the range is a distance between the robot and the feature, and the bearing is a relative angle between the robot heading and the direction to the feature. Now I would like to talk about the motivation of this research. You all know DISA has published an important SLAM paper. It's called A Solution to the SLAM Problem in 2001. And it's the most cited paper, at least in SLAM area. And DISA gives some practical implementation of EKF SLAM algorithm and also prove some convergence properties. The problem of that paper is the proofs is given for the case when the model are linear. So extended Kalman filter using nonlinear process model and the nonlinear observation model, but in the proof of the paper, they assume the models are all linear. So one question to ask is, for nonlinear case, do we still have the same convergence property? So that's one motivation of this work. Another motivation is, at the time I started to work with DISA about SLAM, and DISA told me Paul Newman obtained some strange result in his EKF SLAM simulations. For those who don't know, Paul Newman was a PhD student of Hugh Durant-White and DISA. So DISA was Paul's PhD co-supervisor. So when Paul did some simulations, he found something strange. The strange thing is, if robot starts from a non-zero covariance matrix, the covariance can be reduced after some time. So we know SLAM is simultaneous localization and mapping in an unknown environment. So we know nothing about the environment. And if we see something in an unknown environment, how come the uncertainty of a robot be reduced? So that's very strange. So robot have some uncertainty and it observes some new features. It shouldn't reduce uncertainty of the robot itself. But in reality, in the simulation of EKF, the uncertainty was reduced. That's very strange. And initially, Paul think it's a bug in the code. But after a lot of checking, there's no bug in the code. So it's really something a bit strange. So why this can happen? That's another motivation of this work.
Shoudong, can you explain a little bit why the uncertainty of the robots shouldn't be reduced?
We are talking about traditional SLAM, and traditional SLAM, we are using a global coordinate frame. And when the robot observes the landmarks, the information are all relative. There's no information about the global thing, right? So imagine you don't know your position, and then you see some features, but the features you don't know their position either. How can you improve yourself? It's just impossible, right?
Sorry, Shoudong, so can I understand it in this way? So it's like there is a transformation from a local map to to the real world. And by only observing the local features, we can't reduce any uncertainty between this transformation. Transforming from the local one to the real world.
Yeah, I think that's probably a better explanation. Yes. So normally when we start our extended common filter SLAM, we're starting from the robot starting pose as the origin, right? Then everything is relative to that one. But if you're starting from a different coordinate frame and you don't know the transformation and you have no way to identify those transformations or improve that transformation. Yeah, that's probably a better explanation. Yes, good. So this is the MATLAB code I sent you, and if you run it, you will see something like this figure. So suppose the robot is positioned at 1010, and it has some uncertainty in its position, and also has some uncertainty in its orientation. And it observed two landmarks. One is at 0, 0, another is 25, 0, I think. And then after multiple observations, the variance of the robot orientation error will reduce from 0.03 to 0.0008. So this is what I sent to everyone in the code. So this is a code sent to you. If you run this, so the initial covariance matrix of the robot is this. And the first element is about the orientation. The second and the third element is about the position. So the initial uncertainty is 0.03. And after a few steps, this uncertainty starts to reduce. So step 3, the uncertainty becomes 0.003. And then you keep observing the features, then you will get smaller and smaller variance of this orientation uncertainty. And the green circle shows the uncertainty ellipse of the estimates. So this is something shouldn't happen, because if you don't know the orientation and you see new landmarks, you can't improve your knowledge about orientation. But this EKF SLAM algorithm tells you you can reduce the uncertainty. You have more knowledge about the orientation. So probably at this stage, it looks a bit obvious that this is something wrong. But at that time, it really took me some time to convince myself there's something wrong in this algorithm. And I finally convinced myself in one morning when I sent my wife to a job interview. You probably know I came to Sydney in 2004. And since I came to Sydney, I worked at UTS. It never changed my job, but my wife changed her job many, many times. I can't remember exactly. And he went to job interviews many, many times. That's one morning I sent her to a place, a company to interview. And while she was doing the interview, I was waiting outside. And I just looked at 2 trees and asked myself, if I don't know my orientation and I keep looking at these 2 trees, can I know my orientation or not? Because I did some simulation as well, very similar to Paul Newman, and get the same result. So I'm a bit confused. Sometimes I feel, okay, it's possible, yeah, because you see some landmarks. But then I realized the landmarks are new, right? You don't know the position. Then how can you improve your orientation? So in that morning, during about an hour waiting for my wife, I convinced myself there's something wrong. This shouldn't be correct. So I think then I start to prove something. I see what I can do. So let's look at the convergence of EKF SLAM. That's the first thing I can prove. This is a theorem. It says if the robot is stationary and observe a new landmark n times, then the covariance matrix of the robot pose and the new landmark position estimate is this one. So P0 is the initial robot covariance matrix, which is 3 by 3.
So Shoudong, it's showing your MATLAB window.
Oh, sorry. Yeah, so I kind of believe that this algorithm, there's something wrong there. So I start to prove something. And are you seeing my slides now?
Yeah, all good. Thanks.
So first thing I want to do is I want to prove some convergence properties of this ECAPS lamp. And this is the first result. The result says that if the robot is stationary and observe a new landmark n times, then the correct metric of the robot pose and the new landmark position estimate is this matrix. So P0 is the initial robot covariance, and RA is the observation noise covariance. And this AE and A are part of the Jacobian of the observation model. So P0 is 3 by 3, and this element should be 2 by 2. So the matrix is 5 by 5. So basically we have a clear formulation about what the correct matrix is after n observations of a single landmark. But what we can prove is, we can prove this result only when the Jacobians are evaluated at the ground truth. So if the Jacobians are evaluated at ground truth, we can prove this result. What does the result say? Intuitively, it says that. So suppose robot have this uncertainty, and if it observes the landmark many, many times, the final landmark uncertainty is something similar. But this is only true when the robot orientation uncertainty is small. So robots stay here, observe the landmark many, many times. This is the uncertainty of a robot. And after many, many observations, the uncertainty of the landmark is the same as uncertainty of the robot. But this is only the case when robot orientation uncertainty is small. If the robot orientation uncertainty is large, then after many, many observations, the best you can achieve is this shape. Instead of the same circle, you only have an ellipse. This is because the robot orientation uncertainty is large. And this figure basically is a kind of visualization of this result. When n goes to infinity, this part disappears, and this is what we can get. So when the robot orientation uncertainty is large, this is the best we can achieve. This can be clearly illustrated using this example. Just imagine if I know my global position exactly, and you are 5 meters in front of me, right? And then what is your global position? In the first case, if I have no idea about my orientation, I know you are 5 meters in front of me, then you can be anywhere on the circle besides a radius of 5 meters. And if I know I'm facing southwest approximately, then you will be somewhere here. This is similar to what we have in the ellipse case, because in the extended Kalman filter, we always using Gaussian distributions. So this uncertainty is represented by ellipsoid. If I'm facing southwest exactly, then I would know you are there exactly. There's no uncertainty. So this is the same as what we have proved in the result. We also proved some more convergence property. For example, when robots stay at point A and observe the landmark many times, then move to point B, and then observe landmark many times. In this case, we proved that the Jacobian at point A and Jacobian at point B has a particular relationship. And using that relationship, we can prove the convergence property, which is described in the theorem in the paper. But roughly speaking, it can be shown in this figure. So in this top left figure, the robot stays at point A, observing the landmark many times, and then move to point B, the uncertainty of the landmark doesn't change. And figure A is a case when there's no control noise. And figure C says when there's some control noise. So when there's some control noise, the robot moves to point B, the uncertainty increases. And you keep observing this feature many, many times, then the uncertainty of the robot can reduce to the same level as the case when there's no control noise. But the landmark uncertainty doesn't change. So this is a limit we can achieve. So the result basically saying the uncertainty of the landmarks, this ellipse, that's a limit, and it can never be changed. Even if you change your position to see the landmark again, doesn't help. More of the convergence properties are in the paper. And now I talk about this consistency. The proofs of the convergence properties are only possible when the Jacobians are evaluated as the ground truth. But in practice, in economic filter, the Jacobians are evaluated at the estimated values. And this may cause inconsistency. The inconsistency means the computed convergence matrix by EKF is smaller than the theoretical convergence matrix. Or in another word, the estimate in EKF SLAM is overconfident. This issue has been pointed out by people already. For example, as early as 2001, some people talking about this inconsistency, and also Tim Bailey pointed out this issue as well. And they also clearly pointed out that when the robot orientation uncertainty is small, there's almost no inconsistency. But when the robot orientation uncertainty is large, then this inconsistency can cause serious problems. So in our paper, we kind of analyze this a bit further. And what we found is EKF SLAM can be overconfident mainly because it uses relative information to estimate absolute locations. All the information in SLAM is relative, but we are trying to estimate the absolute positions. And I've used this as an illustrative example. Suppose X and Y are two scalars to be estimated. And suppose we can only measure relative information, which is X minus Y. And suppose we have two measurements with noises. And one measurement saying that one is equal to 99.9. And Z2 is also a measurement of X minus Y, which is 100.2, suppose. If we have these two measurements, it's clear that the only thing we know is X minus Y is around 100. We can't get any other conclusion. We have no idea about the absolute value of X and Y. But suppose we are not talking about the linear system. If we are talking about the nonlinear system, then with nonlinearity there and with linearization error, the first measurement may give us something like this: 1.01x minus y equal to 99.9. And the second one, linearization at a slightly different point, give us 0.99x minus y equal to 100.2. If we have these two equations, then it's possible to obtain the absolute value of X and Y. And this is the wrong information. And this wrong information results in overconfident estimate. this is SLAM problem. How about the case like localization, right? If it's a localization problem, then the landmark is something we know. The only thing we don't know is a robot. Then it's something like this. If the 1D case is something like this, the measurement is like x minus y is 10, for example, 99.9. And second measurement, x minus 10 is 100.2. And suppose there's some linearization error, 1.01x minus 10, 0.99x minus 10, we got two equations like this. These two equations still tells us x is close to 90, right? Close to 110, right? So 110 minus 10 is 100. So this x is around 110. So it's not a big problem. There's no like wrong information there. There's some noise, of course, but you don't have inconsistency. So we use this example, try to illustrate that SLAM problem can have overconfident estimates, but localization problem probably is fine. So this inconsistent issue is kind of a unique property of SLAM problem. So for some detailed analysis about expanded common filter SLAM, we use Jacobians and get some formulas like this. This A1 tilde and A2 tilde are Jacobians, calculated from Jacobians, evaluated at slightly different positions. So if we have two measurements and after do linearization, we will get something like this. And because in EKF, we estimate the Jacobians at different positions, and this A1 tilde, A2 tilde are slightly different. When they are slightly different, we can use those two equations to calculate delta phi, which is the orientation of robot. But if the Jacobians are the same, we are not able to do that. So this is similar to our illustrated example about why EKF SLAM can be inconsistent. We have more detailed analysis about this in the paper, and we talk about the stationary case. We talk about when the robot moves to another point, but a similar thing happens because the Jacobians are evaluated at different positions, and these equations give us some wrong information. This makes the estimates overconfident. So this is an inconsistent issue, right? So if the robot stay here, observe two landmarks. The red ellipse are the limits, theoretical limits. But if we do normal EKF SLAM using the Jacobians evaluate at the estimated values, then we will end up something very small, which is close to a circle. So this is the wrong information gain or inconsistency. And it contradicts with our intuition that you cannot improve your orientation estimate by observing new landmarks. This paper was first accepted by ICRA 2006, and when I present this paper, Paul Newman was there, and he was very surprised, and he really thinks this is a good piece of work. So that's 2007. After 10 years time, my student Teng Zhang and others published another paper, which is convergence and consistency analysis for 3D invariant EKF SLAM. In this paper, they borrowed some ideas from other peoples and prove that using this linearization on this Lie group structure, the consistency of EKF SLAM can be significantly improved. And the next week, my student Yang will talk about this, how this can happen.
Sorry, Shoudong.
Yeah.
May I ask you a question?
Yeah.
So in your previous slides, so I'm wondering if, so here the landmark is just a point, right? So suppose you can see a kind of orientation of the landmark.
Mm-hmm.
So is this gonna be helpful?
I don't think so, because again, the information is relative.
Yep.
Yeah, I think in Yang's work, he's dealing with object features,
yep.
And that object have poses. The same inconsistency happens if we are not doing it properly.
Okay, thanks. Thanks.
Yeah, so this is a work in 2017. I would say it's a good paper because it's already cited nearly 100 times in the last few years. And also recently, Yang has come up with another algorithm, EKF SLAM algorithm, dealing with objects. So the features are objects, are poses. And he used a similar environment EKF to demonstrate much better consistency result. Again, Yang will talk about this next week. Yeah, let's give a summary. This is a kind of old work, but the first point I want to say is EKF SLAM summarize all the previous information in the estimated Gaussian distribution. Gaussian distribution including a state estimate and a convergence matrix. And because we summarized all the information as a Gaussian distribution, we will no longer use the original information again. We don't do linearization using the original information anymore. So if there are any linearization error, then it's there and it can't be changed. So this makes the problem overconfident problem. And the reason is the linearization at different points in different time step, the linearization is taken at different points because the feature position keeps improving and you're changing the linearization point. So people say EKF SLAM inconsistency is because of linearization error, which is correct. But in our current paper, we talk a bit more about why the linearization error can make SLAM problem not good. But for some other problem, like localization, it's still all right. So the EKF SLAM inconsistency from our point of view is because it uses relative information to estimate the state in the global coordinate frame. If we don't use the relative information to estimate the global state, then it should be much better. And because of this kind of research, many people come up with different strategies to improve the EKF SLAM consistency. For example, robot-centric EKF SLAM. For example, the first Jacobian EKF SLAM. But I would say they are not as elegant as invariant EKF that Yang will talk about next week. So those are the summary about this paper. I also write a few dot points about the summary about something in general. So for the first one is, when we find something strange in our experiments or simulation, it's a good thing. When you find something strange, then it's possible that we will discover something very valuable, right? So this EKF SLAM convergence consistency is starting from something strange, right? So when there's something counterintuitive, don't just forget it. Keep looking into that, and it's possible that we will be able to discover something really useful. And also, simulation is a good way to isolate the problem such that we can investigate easily. If we are doing that practical implementation of ECAF SLAM, then you got some errors. You don't know whether it's from the data noise or you're from the wrong data association or many other implementation issues or like synchronization or many others. But if you do simulation, you can clearly isolate the problem. There's no data association issue. You can even use the ground truth as to estimate the Jacobian, to evaluate Jacobian, and many things. You can try many things, and you know ground truth, you know everything. So simulation sometimes is a good way to isolate the problems such that we can investigate one by one easily. Also, I want to say a good paper doesn't need to solve a problem. Sometimes it's good enough to clearly point out a problem. For this paper, I didn't really solve anything. I just clearly point out this should be the theoretical limits of the uncertainty, but in practice, the limits is violated, right? We clearly point out why this can happen, and that can be a good paper. Also, it can take more than 10 years to fix the problem. Like the invariant EKF, after 10 years time, we come up with this idea. Probably we still can't say we completely solve the problem, but sometimes it really takes time to solve an existing problem. The final point I want to say is, it's possible to keep our spouse or partner happy while doing good research. Just imagine that morning when my wife asked me to send him to interview, if I told her that, yeah, I'm very busy on my research, you drive it, drive yourself, go for the interview. Then probably it will end up with a big argument, and I will not be able to come up with this idea. So sometimes keep your partner happy will help your research. Okay, that's all I want to talk about today. Any questions? It's a black swan. Raphael, what do you mean exactly?
The black swan is so when English people came in Australia, they saw black swan and they thought that was like an isolated event. They thought that was an error.
Okay.
And so it's like, and they thought it could not be a thing.
Okay.
And then they discovered black swan afterwards. That it's actually a thing. So it's I think it's a name for when you find something like a bug or something, which seems to be an error, but it's actually there is something hidden behind it.
Yeah, that's good. I think next week, Yang will talk about some new work along this direction. Currently, I think this invariant EKF have a good potential. Although we can't say the EKF SLAM can get the same result as optimization-based result, but it's getting close. And in reality, if we don't have to keep the previous process in the set vector, that will save a lot of computation power. is there a connection here to unbiased estimator? I think currently we are assuming everything is unbiased. So for example, the observation noise, we simulate absolute Gaussian noise, but still this inconsistency can happen. So this is probably, we are still doing it under a kind of ideal scenario, like the noise is not biased, but this inconsistency can still happen. Liang asked, will robot-centric SLAM solve this inconsistency issue? It solves the inconsistency issue to some extent. There's some comparison between robot-centric SLAM and invariant EKF and first Jacobian EKF and others. I think still the invariant EKF performs the best so far. I think Liang and myself have given some talks on our papers. The works are relatively old, and in the future, I think we will ask our students give more presentations on relatively new works. And yeah, maybe some of my work is a bit outdated. I haven't written many good papers recently, but my students have. If no question, we can stop here. And next week, Yang will give another talk along this direction. And after that, we probably go for another topic. We will move to another topic for this reading group.